Hello, welcome to seventh live session of the topology to NPTEL course. This is Shavik, third period scholar from Muslim Mathematics. So, well, so before starting today's topic, so before
Hello, sir.
starting today's topic, let me know do you have any question or conclusion before start and before that, let me know am I audible properly and is the screen visible to you?
Yes, sir. You are audible.
Oh,
I have a question.
yeah,
Why every regular space
yeah.
with countable bases is normal?
Well, okay. So, well, it seems that you have. It's it's good to hear that you have tried to solve some exercises. So this problem is actually some exercise problem, and this not comes from theory part. Okay, so let's try to prove it. Anyway, it's a big theorem anyway, so it's not a little problem. Okay? So hear me out properly, and let me know do you have any confusion in between the argument. Okay, so 1 minute. Well, so what's the question? Sorry, what's the question? Question is that every regular space with countable basis is normal. So for that, what we need to do, we need to start with some regular space of countable basis. So let capital X be a regular space with basis, and let A and B be disjoint, closed subsets of X. Each point X of A has a neighborhood U not intersecting B. So this is one. Okay. Now using regularity, we can choose a neighborhood V of X whose closure lies in it. Now finally choose an element of beta containing X and containing B. By choosing such a basis, element for each X in A, we can construct countable covering of A by open sets whose closures do not intersect. Now, since, well, just observe that till now, whatever I am writing, it is not at all difficult. Just go along with me line by line, and if you have any question, just ask, stop me and ask. Okay. Now, since its covering capital A is countable, so we can index it with positive integers. Let's denote it by U1. Okay. Now, similarly, choose a countable basis. Actually, the collection. Sorry, choose the countable collection Vn of open sets covering B such that each set Vn closure is joined from. So the sets U is equal to union of Un and V is equal to union of Vn are open sets containing A and B. Yes. But of course they are disjoint. Okay. Till now, let me know, do you have any question or a doubt? Till now, let me know, do you have any question or doubt? Okay. Since U and V are open sets containing A and B respectively, that's it, of course, that's right. So, uh, so now, there is the following. There is the trick. What is the trick? The trick is as follows. For n given, define un prime is equal to un minus union of I is equal to 1 minute. 1 minute, I shall get back to you after 2 minutes. So okay, for given n belongs to undefined un dash is equal to un minus I is equal to 1 to n via closure, and vn dash is equal to vn minus un is equal to I to 1 to enclosure. Okay, now note that since each set un dash is open, being the difference between an open set un and a closed set union I is equal to n via closure. And what? And similarly, each vn dash is open, okay, which is obviously by choice. So then the collection, un dash covers the set capital A. Now, since each x in A belongs to un for some n, and x belongs to none of the vi closure, uh, so so what? So the collection vn dash covers V. So the pictorially it is as follows. So pictorially, suppose these are some UIs. Suppose U1, U2, V1, sorry, V2, V3. Okay, this is our A and this is our B. And now, uh, passing through passing through trick, what are we getting? We get something interesting. Here is our U. Here is our this. This is one. This is and the third one. So this is our U1 dash, this is our U2 dash, this is U1 dash. Yes, okay. And so this is our this and this are our here, okay. But now the whole thing becomes this. So after the above trick, so the above trick gives following open source, namely so this gives the sets u prime is equal to un dash n belongs to c plus v dash un v dash n belongs to c plus. Okay, and are disjoint. Okay, now for if x belongs to u dash intersection of v dash, then what happens? Well, so for if x belongs to u dash intersection of v dash, then of course x belongs to by construction uj prime intersection vk prime for some j and k by construction. And now suppose j less than equal. So it follows that x belongs to uj and j less than equal. And this implies x does not belong to uj quotient. So and of course a similar contradiction arise if j less than equal to j. Okay. So this is the whole argument. So what we have seen from the argument. Well, so basically, well, so this argument is actually what. So basically, what we have seen from the argument. So basically, we have chosen open sets U, G, and we have open set will be three, and we need to make this those join by some technique. And A and B are to close the side that now we had made it by using that trick. Okay, so I mean, so this is the whole argument. Well, if you go through the argument, it is not really difficult to understand what it is. So it is not really difficult to understand the solution, but well, as expected, the solution is quite tricky. So you need to practice a lot in order to master this thing. So that is the only thing you need to do from your side anyway. So that is the argument. So this says that a regular space counter base is normal. Okay. So, Mustaq, so this argument. Now, let me know. Do you have any question or doubt? I understand the solution is big, so it might time to understand the whole solution. But anyway, no problem. You can drop an email or you can ask your related question in the next live session. Okay. So, so one. Hello, sir. Hello. Yes, sir. Sir, 1 minute, sir. Actually, right now I'm in NPT live session, 2 hours. So I will call you, sir, after 9 p.m. Okay, sir. Okay, sir. Okay, sir. Okay. Oh, well. So, Mustaq, let me know. Do you have any question or doubt, or else we can go for some questions, or if you have a doubt, you can ask me, or else I have some questions to solve. Anyway, okay. So uh, I hope this is very much clear to you. Now,
Okay, sir. Okay.
okay,
I will go through that.
okay, okay. So, okay. So So if you have any question, you can ask, or else I can start with some problem solving. So, well, so the first problem is as follows. So the question: show that Gibbs extension theorem implies variations. So how to be? So tell me. Okay, I mean, no need. So okay, so recall that. Okay. So what is the statement of Wilson's lemma? Wilson's lemma tells that if you have a normal space and you have to close our space A and B which are disjoint, you can get a function little f from x to 0, 1 such that you can send the whole closed set capital F to 0 and send the entirely closed set capital B to 1. Okay, now, so and this tilde extension theorem is saying what? Saying that if you have a normal space and if A is a closed subspace of A, so if you consider a continuous point from capital A to either closed subspace of real line or consider the whole real line, you can the function, we can extend the function to whole of x. Now using the, of course, from the statement physics, so we need to get the statement Vision's lemma. So how to proceed? Oh well. So for that, what I need to do? So suppose capital X be a normal space and let A be to close disjoint subspace, etc. So now first consider a function to A union B to 0 comma 1, sending A goes to fully 0, B goes to fully 1. Okay. Okay. Now, of course, this is continuous. So now extend f to whole of x. Call it f tilde. That is f tilde from x to 0 comma 1 such that f tilde capital A is equal to f of A is equal to 0 and f tilde capital B is equal to f of A is equal to 1. And this is nothing but Position's lemma, right? So this is the argument. So That's how rejection theorem implies origin. Okay, now let me know the question or confusion. Well, now, uh, well, um, so the next question is the following. So in the topological space, we have seen the Wilson's lemma, which I mean, of course, we have not seen the proof, but believe me, the proof is too long because the proof is somewhere specific. Okay, it's not just somebody. We should respect him. This proof was due to the PhD thesis of Wilson's. I mean, it's total PhD work. So that's why one can expect the proof is very big. So that's why for the exam point of view and your time constraint, we're not getting into the proof right now. But for metric space, there is a easy proof for this. So of course, one can apply the Wilson's lemma proof in the metric space, but of course, there is already easy proof in the metric space. Actually, the Wilson's lemma proof for metric space has been done before the Wilson's lemma in the topological space. Okay, so uh, so question is prove Wilson's lemma in metric spaces. How to do it? Think about it and let me know. Well, so yeah, it's quite tricky also. That's why it's not that close. But anyway, let me solve it for you. So what? So let A and B be closed. Subspace of X. And obvious are disjoint. It is important. Now define. Yeah. X. dAx by dAx plus dBx. Okay. So now dAx equal for x belongs to x. dx equal to 0 if and only if x belongs to a, and dby equal to 0 if and only if y belongs to b. So this implies f of a is equal to 0 and f of b equal to 1. Okay. So this tells that f is a function from x to close 0 1, sending a goes to fully 0 and b goes to fully 1. Okay. So that so this is nothing but this is nothing but Urishans lemma. Okay. Right. Okay. So now, well, hold a minute. Let me solve the question. So, Well, so now let's go for the next question. Let X be a metric space. Show that so let X be a metric space. Show that following are equivalent. First one, X is bounded under every metric that gives the topology of X. Every condition of P from X to a bounded. Third is X is the limit point function. Hmm. So now how to proceed? Think about it. I shall wait for 2-3 minutes and let me know, are you able to solve anyway? Then I shall solve it for you. So let me know, do you have any
Hello, sir.
idea how to? Yeah, Mr. Sunny.
Can you kindly explain why compact house drops is normal?
Ah well, ah well. So so your question is that why compact house is normal? Okay. So let's try to solve it. Why compact house is normal? So, well, this solution is tricky. We have seen something like in the while studying the compared space. So, so we'll assume some results from there because we are directly possible to prove everything from scratch. Okay. So, let capital X be a compact whole. So we have already proved, we have seen if A subset of X is closed and X subset A, then there is open sets U P of X with A intersection B such that X belongs to B and A subset of U. Okay. So now, so uh, okay. So now what we can do? We can uh, okay. So now let A and B be to this joint closed sets of X. Okay. So for each V belongs to B, there exist open sets UV PB with UV intersection PB UV contains B and PB is subset of it. Okay. Now put V is equal to intersection PB and okay. Now so obviously this collection UV covers First things, low subspace of compact space is again compact. So, uh, so finite subcollection of UV coverage. So let B is equal to union of UVI is equal to 1 to n. Now put V is equal to intersection UVI is equal to 1 to n. Then V contains A, and of course by construction. Okay, and the construction, of course, V intersection UM, and of course U30. So basically, so this is what the normality. So this is what we get normal. Okay. So basically, Mustaq, if you look at the argument, it technically is nothing. Basically, so there is
Yeah, I follow. This is the true by forward. And
yeah. So if you observe that actually the solution is not difficult for compact space, there is already some theorem, and we simply need to extend the theorem for two closed space. Okay, so that's all. So tell me, do you understand the argument? Mustaq, tell me, do you understand argument? Okay, okay, I hope so. You have understood the argument. So now let's well. So now, okay. So now let's go back to the original question. So the question was that suppose X be a metric space and show that the following equivalent. Suppose X is a bounded under a matrix that gives a topology of every continuous function P extra bounded X a limited compact. Okay. Well, so so let's see. So um, what? Observe that. Observe that. For metric space, point number 3 or the condition 3 is equivalent to being compact and implies a compact metric space is bounded and continuous image of a compact continuous image with compact, so it's compact. Okay, now point number 2 gives one. How? So fix a point and the function from x goes to dxa is continuous function. So now 2 also gives 3. How if an infinite curve space has no limit points, then it is closed and discrete. And a surjective function from it on the set of positive integers is continuous and can be extended to a continuous unbounded function. That is, the space is metrizable and so normal. So is normal. Now only left to show that one gives 2 or 3. Now for 1 gives 2, there is a trick which is needed to be used. Okay, what I want to do, the trick is the following. The trick is the following. If phi from x to r is continuous, function, then f of x is x marked by x is embedding of x in x cross r. Now if a finite subset of x having no limit point, then it will be surjection of A onto Z plus. Okay, so this is the whole argument. So so basically the point, so it's so well, so the I mean, so you can remember this thing that metrizable space being linear compact is equivalent to say independent function bounded, because the metric space all these things are equivalent. So so uh, so now let's go to the next question. Well, now the next question. Well, so the question is that show that xn minus 1 is retract of Rn. So So I think I should recall the definitions. So what does retract mean? Retract means so X be a space, capital B a closer space with capital X, we say to be retract or capital X if there is continuous function little r from X to A such that little r restricted to capital A is the identity on it. Okay, then X is said to be retract on X. Okay, so this well so so we can define retract from R to L minus 1 by sending x equals to x by non. That's correct. And why this will happen? This way, so I mean, sorry, because R raised to Sn is equal to Pi identity on Sn minus 1. So this works, okay. Now the next question. E um, can open 0, 1 be retract of real line? Can open 0, 1 be retract of real line? So, so the answer is of course not. But you need to prove it why it's possible. That is why there cannot be any such function little r from real line to open 0, 1 such that the function restricted to the interval open 0, 1 is equal to the given is equal to the identity map on open 0, 1. Now we need to prove that why such a situation is not possible. Okay, yeah. Well, so um, so you need to consider the non-existence of such type of function by using. I mean, you need to prove this by using some kind of sequential criteria under the continuity. That is, if the sequence x n goes to x, then f of x n must goes to f of x. You need to use this sequential pattern in order to show such a function cannot exist. So it doesn't exist. Think about it. Oh well. So suppose there exists a continuous function R from R to open 0, 1. So the real line restricted to open 0, 1 is identity map open 0, 1. Okay. Now, choose a sequence one by n. Consider a sequence. Of course, this sequence lies in open 0, 1 and this sequence goes to 0. So this is f of 1 by n equals to f of 0, correct? But f of 1 by n is equal to 1 by n. So these two implies what? This 2 and this sequence goes to 0. So this implies what? F of 0 goes to 0. So this implies what? 0 belongs to image of f. But it is not possible. Why? Since codomain of f is equal to only open 0, 1. So these are. Suppose there is a continuous function f from R to 0, 1. So the R restricted open 0 identity of 0, 1. No one goes to f of so this means what? The 0 belongs to what is not possible. So that is the argument. Okay. So so 1 minute. So that's why open 0 cannot be refract of real line. Okay. Now, oh guys, please hold on. I shall get back to you in a few minutes. Well, so, well. So I hope this answer is clear to all of you. Now let's go to the next question. Okay, so mm, okay, wait. Okay, so now it's a quite interesting question to ask that provide an example showing that a house door space with counter basis need not be meterizable. A house door space with counter basis need not be meterizable. Okay, so what is the possible example? So we need to consider a household space. So I mean, okay, so there are a lot not. I mean, okay, so it has to be second countable. So one can choose the R with real limit to fall, R with lower limit to fall. So RL is one such space, okay, and of course it is house drop. But it is, of course, it is not. But it is not meterizable. Why not metrizable? Since if it is second countable, so being metrizable implies it's Lindelof, but it is not the case. So so R will be element topology is Hausdorff countable space on space is better metrizable. Okay, so this makes sense. Now, well, so now let's get back one pending proof, namely what? Well,
No, sir.
yeah, Mr. Primi.
Can you explain how TJ extension theorem implies Euroson's lemma?
Well, so one minute. So we have already discussed uh, this, I guess, yeah. So look into the screen. So for the Tuesday extension theorem, we what is the statement? The statement is that suppose the given space is a normal space and we have some closed out space, then any continuous map from the closed out space to either closed interval or the whole of real line, then this map can extend it to whole of capital X. And Wilson's lemma is saying what? Wilson's lemma is saying is that if you have any normal space and if you have any closed disjoints also, you can have a function little f from x to 0 comma 1 such that the function little f sends the whole set capital A to single point 0 and the whole set capital B to single point 1. Now, in order to use this extension theorem to prove the Wilson's lemma, what we need to do? We choose some disjoint closed open subspace of capital X uh, and now we have some. So now we can construct a function from A union B to 0 comma 1, which sends the A goes to singleton 0 and B goes to singleton 1. Of course, it's continuous because they are disjoint. Now this map A can be extended to whole of capital is called F tilde. And F tilde is a map from X to 0 comma 1. So the F tilde of capital A is 0 and F tilde of capital B is 1. So this is what the Wilson lemma is. How do you understand? Mustak, let me know. How do you understand?
Yes, yes. I understand.
Oh, well, well. So now, uh, Well, now what else? Now we are in a position to prove the equation. Sorry, we are in a position to prove that R with lower limit topology is lambda. R with lower limit topology is lambda. So in order to show something, then what we need to? We need to prove what? We need to prove that every open cover has countable subcover. Correct? This is what we need. Every open cover has countable subcover. So let A alpha B alpha be a covering of RL by base elements. We want to find we want to find countable subcollection coverings. We want countable subcollection coverings. Okay. Now let C be the set union. Alpha belongs to J. A alpha B alpha. Which is a subset of we Then show R minus C is countable. Okay. So wait a minute. Well, oh shit. Well, sorry, mistakenly my pen fallen from hand. Kindly hold a minute, please. Well, so we will show that R minus is countable. So how to do it? So let x belongs to R minus. Okay, I mean, how to read means it's actually quite tricky to solve. It is not obvious. The solution is not also obvious. Okay, then argument is quite counterintuitive. So you need to practice this problem in order to the result, in order to write well in exams. Okay, so let's take the point on this. We know that x belongs to no open interval a alpha b alpha. So x equal to a beta for some. Now choose such a bit and then choose qx to be rational number belonging to the interval a beta b beta. Now since this interval a beta b beta is contained in C, so if the interval a beta qx equal to x qx. So it tells what? So this tells that if x and y belongs to r minus c and x not equal to y, with x less than y, then qx less than qy. Why? Because otherwise x less than y less than qy less than equal to qx. So that y would lie in the interval and hence it's therefore the map x goes to qx r minus c into q is objective. So r minus is countable. So this tells the countable argument of r minus. Okay. So r minus is countable. Oh, now we show that some countable subcollection of A covers are. To begin, choose for each element of R minus. Nth element of A containing it. One obtains a countable subcollection A prime of A covers R minus. Now take now take the set C and well, now take the set C and topologize it as sources of R. Now, so basically what we are changing is topology. Now, in the new topology, C satisfies second countable reaction. Okay. Now, C is covered by the sets A alpha, B alpha, which are open in R and hence open in C. Then some countable subcollection covers C. Now, suppose this subcollection consists of elements A alpha, B alpha for alpha equal to alpha 1, alpha 2. Then the collection A double prime, which is A alpha, B alpha with alpha goes to alpha 1, alpha 2. This collection is a countable subcollection of A that covers the set
Sir,
C.
please kindly repeat.
Oh well. So, Mr. Can you please tell from where you asked me to repeat? or you want to repeat the whole argument? Which one? Oh well, let me finish my line. So, since A prime and A dot is a countable subcollection, after just finishing the line, I will repeat. A that covers Rn. So, so so basically, this proof is quite tricky. So, in order to show Lindelof, what we need to do, we um, had to 1 minute. So, in order to show that is, we need to choose an open horizontal count example, right? Now, we need to find now. So capital A and B. So we choose initially capital A, closed A alpha, open B alpha by base element is open cover. So the advantage of the base element is that this technique will work with any operator. Because any operator can be anyway as um, union of this type of sets, right? Now, hmm, one. Now we can show the R minus C is countable, right? So we can show the R minus C is countable. So for that, now we are choosing some x from we can choose we choosing x from R minus C. And now since x belongs so of course so x does not belong to any of the open intervals, so the x equal to a alpha for some index beta. Now we can choose a beta and then we choose qx to be the rational numbers belong to interval a beta, since that open interval a beta comma b beta subset of C, so is the interval a beta comma qx. And this tells that if x and y are in the complement of C and they are not equal with x less than y, then that corresponding association is also not equal. That is, qx is also less than q1y. There is it's kind of increasing. Now other so this is the argument now. So this tells the map x goes to qx from R minus C to q is injective, and this tells that R minus C is countable. And okay, so this tells the R minus C is countable. Now for using this technique, and then we are going to associate one. Now then we are going to assume some topology on the set capital C, and then we are under the new topology which we are giving capitals under that topology the C transfer the same countable actions, okay. And then we are now we can observe that the under the new topology the new topology is what's that than the original low limit topology. See in the fourth topology space is second countable, so sorry Lindelof, so the final topology also the space is Lindelof. So that is the argument, okay. So yeah, so this is the argument. So Mustaq, let me know. Yeah, are you able to understand the argument? Okay, I mean it's okay if you are not understand by it. But the point is that you need to go through the argument and you need to write the argument line by line in order to make it clear. I mean crystal clear. Okay. I mean anyway, this type of thing is not expected to come in exam, but if you want to understand and learn this thing, then this type of argument you need to grasp a lot. Okay. Okay. So that's all for today. Okay. So that's all for today. Uh, I am leaving the session. Thank you. We shall meet. We shall meet on the next Friday.
Thank you.